Today, I'll be talking about some recent work of ours on explaining heterogeneity in medial entorhinal cortex with task-driven neural networks. The ability to self-localize in the environment and to update one's position on the basis of self-motion are core components of navigation. Animals have a remarkable ability to do that. Central to this is a spatial representation system that contains place cells in the hippocampus, which become active when an animal enters a particular place in its environment, as well as grid cells, border cells, head direction cells, among others, in medial entorhinal cortex, or MEC. So, for example, grid cells exhibit periodic firing fields forming a regular triangular grid across the environment, and they're thought to be generated by path integration as part of a neural map of self-location. However, grid cells aren't the only cells in a medial entorhinal cortex and actually only make up about 20%. Border cells make up about 10%. And a large fraction of these cells actually have very heterogeneous and unconventional tuning patterns that are less obviously well described in terms of simple stereotypical tuning curves, and we'll call these heterogeneous cells. So how might we go about characterizing the response patterns of these heterogeneous cells? And moreover, what functional roles do these cells serve in the circuit, if any? And moreover, as an added measured note of complexity, MEC actually remaps in the presence of reward. So what might further describe the joint interaction between these heterogeneous cells and reward? So our end goal will actually be to have a unified model that can simultaneously explain the different types of neural responses in MEC. And a natural question is where might we begin? Recent work has demonstrated that actually task-driven neural networks can develop these cells by virtue of being trained on a path integration task, wherein they take velocity inputs and report their self-location at each time point. And their internal units develop things that look like, at least qualitatively, grid cells, band cells, border cells, and regular cells. But the natural question is, are they a good quantitative model of these responses? And the reason why this is non-trivial is that there's a lot of ways to have different types of heterogeneity than different types of more structured patterns like grid cell responses. And what we'll show is actually this is non-trivial, that not all models are equal. So how might we go about describing or defining similarity when we can't really describe these heterogeneous responses in words? Well, our approach will be a goal-driven approach, whereby we tune two knobs of behavior as characterized by a loss function data set and circuit as characterized by an architecture class. But before we even can start with the modeling, how can we even measure if a model is correct? And so our approach will actually be to measure consistency of responses between animals. And what we see is that actually when we obtain the right measure of similarity between response patterns in cells across MEC, they're all, relatively speaking, highly reliable. And so therefore, these heterogeneous cells specifically themselves aren't simply noise, but are actually very structured targets of explanation in and of themselves, even if we can't describe them in words. So now we're going to go about actually defining these constraints that would give rise to these reliable responses. So we'll start with the intra-animal consistency as measured by a transform between animals, and we're going to apply that same transform to model features. And what we see at the outset is that actually task-optimized models approach the noise ceiling of these responses quite reliably. And we'll now dive into the ingredients and make them well. Specifically, a non-negativity constraint in the form of a ReLU, along with a gating in the RNN, actually aids in generalization across environments. And crucially, this non-negativity constraint mustn't saturate either. So things like sigmoid are not as good as ReLU in generalization across environments. And furthermore, the models themselves add a lot of predictive power to their inputs, to their velocity inputs. And path integrating with an intermediate place cell supervision actually provides better generalization across environments than direct supervision of position alone, the 2D Cartesian coordinates. However, this place cell representation itself, in and of itself, is not a good predictor of MEC, which is a good sanity check. And furthermore, dimensionality reduction on place cells in the form of non-negative matrix factorization is not a good predictor of MEC either. And just as a note, this non-negative, these NMF models were inspired, especially low-ranked ones, to basically get at things that look specifically targeted towards grid cells. Now, given that we have a model that exhibits close similarity, MEC, we can also use it to generate predictions for experiments that are otherwise very difficult to do. So we focused on knockout experiments. And we see that actually when we knock out units on the order of several hundred, which corresponds to the same definitions that are used to define border and grid cells, network performance is actually relatively robust in knockouts of that size. And furthermore, the heterogeneous knockout, which is a random sample of the same number for each definition of grid and border cell, gives a similar performance degradation as the cell type specific knockouts, especially as the threshold increases. So now we turn to accounting for rewards, as I mentioned earlier. We think that non-spatial rewards are actually part of the same underlying framework. And specifically, we want to capture the remapping that occurs between environments when a reward is present. And the way we go about modeling this is that there's a reward zone in the center of the arena, and the agent can explore this initially, and this is what we did previously, just random walks in this environment. And we see that that actually matches each condition separately. However, it fails to capture the remapping when compared across both the open field and the reward condition. And simply, augmenting the inputs to just be a Boolean when there is a reward or not doesn't help either. So something else needs to be done. So we actually turned to animal behavior, and we took into account the observation that animals tend to take rapid direct paths to the reward zone when it's present. And we modeled this as a change in the policy of the network. And crucially, just simply by just changing the policy but keeping the weights fixed, this is the same model, we can actually improve this quite strongly. And purely exploiting doesn't really help either. However, the best kind of final model is one that titrates between exploration and exploitation in order to capture this remapping. So a reward bias path integrator can capture this. So in conclusion, we see that heterogeneous cells are actually reliable under a suitably chosen transform class. And the classic theoretical NMF model doesn't quantifiably explain all the data. We see a differentiation at the level of task, both navigational training and NMF, circuit differentiation, and account for non-spatial rewards, and they tend with the reward bias path integrator. Overall, we see that normative explanation for grid and non-grid cells can be given, and we put our code online. And with that, I'd like to thank my collaborators and thank you for listening.